Hello, everyone. Let's do more examples of integration by parts. So my next example is the integral of 3x times e to the 5x dx. So here there's a lot of action going on. We have a product. 5x is inside the exponent of the exponential function. So this is clearly not basic. What about substitution? The only maybe interesting idea here would be to use 5x as a use substitution. But if you try it for fun, you will see that this is not going to change the complexity of this problem. What I mean by this is that this problem is the product of two different type of equation, a polynomial of degree 1 times an exponential function. And if you try that use substitution, it's not going to simplify. It's going to stay very similar to this form. So I'm going to use the only other technique that we know, which is by parts. So here we have the product of three terms. We have 3x, the polynomial degree 1, multiplying the exponential term, multiplying the differential term. So remember, for by part really starts like a double substitution. So part of the formula will go inside u, okay, and part of the formula will go inside dv. And here I'm going to use an approach very similar to the previous example. I'm going to use the polynomial for the function inside u, and I'm going to use the exponential function again for the function inside dv. And remember, the differential term dx is always, for every single question by parts, paired with dv. And now you have to compute du over dx by computing the derivative of 3x, which is just 3. But instead of writing du over dx equal to 3, I like to write du is equal to 3 dx. So breaking that differential fraction and just write the dx at the end. It just simplifies slightly the computations here, or the notation behind the computation. Anyways, so what about v? So for v, I need to integrate. Nice. I have to integrate e to the 5x. I know ex is ex, but now I have e to the power of a linear function. I'm going to use my linear trick, which will give me e to the 5x again, but you have to divide by the slope, which is 5x. Before moving forward, I like to always do that little circle of life here, just to make sure that everything is done correctly. So from u to du, there's a derivative. Derivative of 3x is indeed 3, so that's correct. And then if I continue my circle, the derivative of v, which is e to the 5x over 5, if you do a mini chain rule, you're going to get e to the 5x times 5. So by chain rule over 5, the two 5's will cancel each other, getting back your dv formula. So I know that everything in the box here is computed correctly. First and foremost, everything is inside u and dv. My three terms are to be found inside u and dv. And when I compute derivative of u and derivative of v, my circle of life is complete. So now I apply my formula. So it's u first. So here u is simply 3x times v, which is e to the 5x over 5, minus the integral of everything that is freshly computed here. So minus the integral of v, which is e to the 5x over 5, times du, which is 3 dx. So I need a differential term with my integral. And here, look at this brand new integral. This brand new integral has a bunch of coefficient, but x is inside an exponential function. This integral is simpler. There's a good chance that I've done my work correctly. So let's do that final integral here. So here, if I integrate, I get, so here, let me just rewrite the first part. So e to the 3x e to the 5x over 5. And now if I integrate e to the 5x again, I'm going to get e to the 5x again, but I need to divide by 5, but be careful, there's already a 5 there. So by dividing by 5, these two 5's will multiply each other. 5 times 5 is 25 times 3 plus c. So if you are rewriting this cleanly, you don't have to, but normally you write the coefficient first. So the 3 and the 5 would be together. X e to the 5x minus 3 over 25 e to the 5x plus c. And that's your final answer. Let's do one more example. All right, our next example is a little bit more annoying. We have the integral of x squared multiplying e to the 2x dx. Again, product of two things. Again, there's a 2x inside the exponent. If you try a substitution, the only thing interesting would be maybe trying the exponent of the exponential function. But this function is a product of two different things. So we have our nice exponential function multiplying a polynomial of degree 2. So if you try to do that substitution, it's not going to change the type of equation that you're going to get. So here we go. Let's go by part. So we have, again, three terms: x squared multiplying the exponential function e to the 2x, multiplying the differential term dx. Again, you need to take these three terms and distribute them between u and dv. So again, I'm going to keep the same strategy. I'm going to use x squared for u, and I'm going to use the exponential function e to the 2x times dx inside dv. So all my three terms are inside u and dv respectively. Again, the dx, the differential term, is always inside dv. So now let's compute du over dx. The derivative of x squared is 2x. So if you cross multiply and you bring the dx on the right, you get that du is equal to 2x times dx. And then if you integrate e to the 2x, because the exponent is linear, you're going to get e to the 2x divided by 2 using my trick again to get this v computation going quickly. And again, here, it's a good exercise to verify that this circle of life is complete. The derivative of x squared is 2x, and the derivative of e to the power 2x over 2 is e to the power 2x times 2 over 2, which will cancel each other and giving me back the equation inside dv, e to the 2x. So, all right, let's go. So now let's apply what's in the box. And with my formula, so uv, so you get x squared times e to the 2x over 2 minus the integral of the product of the two things I freshly computed. So v, which is e to the 2x divided by 2 times 2x dx. So that's my du. And now look at this formula. It's still the product of two things. I'm actually going to clean it first just to make it more beautiful. So here I have x squared. So x squared, because I see that the two are canceling each other too. So e to the 2x over 2. Those two 2's are canceling each other. And I like to put the polynomial first. So it's x times e to the 2x. All right, so let's look at this dx, this new integral. So we still have that exponential term. We still have a polynomial, but now the polynomial is of degree 1. So we started with a product of degree 2 times exponential. Now we have a degree 1 times an exponential. Question is not over, but it is actually simpler. So I am going to use, again, by part. This is not basic. If you try use substitution, it's not going to work. This question, of course, this new question, and the question is very similar to my previous example, a degree 1 times an exponential. So I'm going to use another by parts. I'm going to use, so again here I have three terms. I'm going to use again by part. So u is going to be again my polynomial. My dv is going to be again my exponential terms times dx always. I'm going to compute du, derivative of x is just 1 times dx, and a primitive for e to the 2x using that infamous trick again. Get e to the 2x again over 2. And you can verify that this circle of life is well balanced. So this is my second u substitution. Not u substitution, that's my second by part that I'm going to use here and apply for that brand new formula. Be careful, there's a minus up front. It's very easy to make a small mistake here. So when you are applying this formula, so the first term is unchanged, x squared e to the 2x over 2 minus, let's open a fat bracket, let's apply the formula. So this is what I'm doing here with this equality. So it's uv, so it's x e to the 2x over 2 minus the integral of everything freshly computed. So we get e to the 2x over 2 times 1. I'm going to write the 1 times dx. So just take your time. It's not too difficult here. So I'm going to distribute my minus, and then I'm going to do my integral. And again here, just a small remark. If you look at my last integral to compute, right here, now we only have an exponential function. So we went from degree 2 to exponential. We apply by parts. We got degree 1 times an exponential. We apply by parts again. And then now we have a simpler integral to compute, and it's just an exponential function. So here, I'm going to simply do my integral, and I'm also going to distribute the minus. So here I get first term is unchanged, so x squared e to the 2x over 2 minus x e to the 2x over 2. Then remember, I'm distributing the minus inside here. So the minus will be a plus. And as I'm doing my integral for e to the 2x, I'm going to get e to the 2x again over 2. So e to the 2x over 2, but there's already an over 2 downstairs here. So it's going to be over 2 times 2. So that's an over 4. And then you sign your work with this nice plus c. And that's the answer for that integral. So notice that we started with degree 2 times an exponential, and we did by parts twice. In my previous 2 examples, we had a degree 1 times an exponential, and we had to use by parts only once. So I want to end this video with this remark in mind that I have highlighted here with my nice little star flying around. If you are trying to solve a indefinite integral, and you know it's not basic, and you know it's not by substitution, and you're trying to do it by part, if your integral is the product of px, where px is a polynomial of degree n, times an exponential function, it could also be times a trig function, sine or cosine, but for us, it's going to be times an exponential function, then you're always going to be using by part, where the u is always going to be your polynomial, and your dv is always going to be your exponential function with the dx, always, always. And you will apply the by parts formula how many times? N times, where n is the degree of your polynomial. My first 2 examples of this section, we had a degree 1 times an exponential, and we did that question using by parts once. And then my previous example, the one we just freshly did, it was a degree 2 times an exponential, and we have to do it twice. So this is a nice little trick to remember, especially in this course where the functions that we're dealing with are a bit limited to exponential, logarithmic, and polynomials or power functions. So polynomial times exponential, assuming we are trying to solve it by parts, always try basic stuff first and use substitution. So this remark is really within the realm of, okay, I am doing it by part. So u is your polynomial, dv is your exponential function, do this n times. All right, so for this video, that's it. That's all. Bye-bye.